Okay, Lecture 10, Equilibrium Constant, Part 1 of 2. So this is a pretty extensive subject. I'm going to have two different lectures here. Here are the terms you should know. First thing is, we need to be able to take any reaction and create the Kc expression from it. So Kc for this one, let's just dive right in. We take the concentration of the products raised to their coefficients multiplied together, since there's only one, that's it. But for the reactants, we take their concentrations. Square brackets indicate concentrations, parentheses don't. Curly brackets don't, it has to be square brackets raised to their coefficients and multiplied together, not added. See that a lot on the exams, have to be multiplied. They're all gases, so everything is good there. Kc here for this next one, trying to write fast, but I want to make sure that they look like square brackets. Each product in square brackets, or fairly square brackets, raised to their coefficients over reactants in square brackets raised to their coefficients. There's only one, then one reactant, then just one term. We only count gases or aqueous. That's the reason is covered very well in the book, and I do it much more I do much more involved explanation in class. But the reason that we don't use liquids or solids in Kc expressions is that their concentrations or densities don't change. So they're just constants. So there's no reason to put in something as a variable that never changes. So we leave them off. So only gases and aqueous have concentrations that will change to any extent during a reaction. So we leave off solids and liquids. There we are for this one. They're all gases, so we're fine. Let's do the next one here. And you should pause and try to do it yourself. Because I know I got this, Dr. C. I'm going to just sit back. So try it. Might as well try it out and get used to doing these. Even if you see them, you have to do them on the exam. And then here's a liquid. We leave that one off. Its concentration, and concentration is moles per liter. We can change that to grams per liter. So grams per liter is a form of concentration. So is grams per mil, which is density. So density and concentration can be interchanged. So since the density of a liquid doesn't change, even though we are reacting it, we're using some of it up, its density remains the same. So it's a constant, so we don't put it into an expression with variables. So we leave off solids and liquids. For this one, Kc, H3O plus squared, got that 2 there, SO4 2 minus over H2SO4. We leave off the liquid again. Okay, make sure I got everything right. I'm going to move pretty fast on these. You should be able to do these in your sleep by the time we get to the exam. Because you have to do this each time we do one of these calculations we're about to do. So once we've done this as kind of just this little simple exercise, then you start to apply these later on. The solids don't count. Their concentrations don't change, so we don't put them into the expression. And then this one here, there's only one gas. The other two are solids, so this is Kc 1 over the concentration. Don't leave this as 0. It's not. It's 1 over the reactants. And then Kc here, just the gas. This liquid is left off. So we don't have water over water. It's water vapor over nothing. It's over 1. I mean, I guess you could do that, but it's just like so. Now let's apply this. Don't spend a lot of time on it because it's fairly straightforward. Lots of stuff in the book on this, but then we use this same method, or we use the Kc expression for every one of these reactions in some way or another. So all these problems that we're about to do, we're going to be using the Kc expression. We're going to have to find it. So the first thing is, Kc for this expression is, or for this reaction is this. Hydrogen there. They're square brackets, so that means moles per liter. Whenever you see the square brackets, that means concentration, and we always use units of moles per liter. Well, they said that we have 2 moles of CO, 4 moles of hydrogen, and 1 mole of methane at the end for 5 liter in a 5-liter vessel. So we're going to need concentrations. So we need to take moles divided by the volume. That's why they put the volume in here. They'll give you everything in terms of moles, and then you have to find the concentration. So we have our reaction. I'll leave off the phases. And if you're working this through on the exam, I don't mind if you do that either. Just be careful, because in this case they're all gases, so they all count. Just make sure that you know what your, if this was liquid, you'd want, and you leave off the phase, you might get mixed up, so you want to be careful. Now, initially, the concentration of CO, well, the initial concentration of CO, let me see if I can fit it on here, is going to be 2 moles over 5 liters, or 0.4 molar. Just verify. So this is 0.4 molar, capital M. No longer moles there. We're dealing with Kc now. We're going to have to be in molars, moles per liter, so might as well change it over. Now we have 4 moles of hydrogen, so 4 moles divided by 5 liters gives us 0.8 molar, capital M. They gave us nothing to start with for either of these. Now we have minus x, minus 3x. Let's see. Is that right? Yeah. And then plus x, plus x. Now we're in terms of concentration. Get used to this, because even though we used moles before, most of the time we're going to be using moles per liter for the rest of this chapter and the next. And actually 3 chapters after this. So this is our equilibrium concentrations, and they say that equilibrium, this reaction vessel contains 1 mole of methane. So our concentration of methane, which is X, is going to be equal to 1 mole over 5 liters, and so that's going to be 0.2 molar. Okay, so that's our X. Now that value has to go in here, whoops, here, 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 and here to determine the final concentrations of all of the species. So once you find X, you're not done. You then have to plug everything in. So we do that, we end up with 0.2 molar CO, and that's 0.2, so this would be 0.2 molar H2. Is that right? I know it's right, but it just seemed odd that came up the same. And then 0.2 for methane. That was just by chance that I picked those numbers. Of course, I had to pick numbers that give you values that appear to mean something other than they're just how they turned out. They didn't have to all be the same. They just turned out that way. Now I should say that on these problems, this is one of the shorter ones that we're going to do. Sometimes I might have to go to a separate sheet of paper, and so if I go off screen, that's okay. I will eventually show everything, and what I'd like to do at the end is just go back through and just have you just scroll through. We make the Kc expression, and now we have the concentrations of the species, and I stopped there because that's what I thought we were after, but it's not. We want the numerical value of Kc, and kind of knew that because I wrote Kc before. So we have our concentrations. Thought we were done with these are pretty large problems, and so that was a lot of work just to get to the point where we now put these values in. Now once you have the concentrations in moles per liter, then we do something funny. We leave off the units. The reason we do is that these coefficients, or these exponents, can be anything. So we could have, we might end up with molars squared, and then molars to the 4th here. So we'd end up with molars to the -2. But it could be, you could end up with molars to any power, and we don't want to worry about that. We just want the numerical value. So what you do is, once you have everything in terms of moles per liter, then leave the units off. if you don't carry them through, if you don't do that and you carry them through, you'll find that yeah, you try it. You'll just see that it gets to be pretty intensely complicated. And this turns out to be 25. Let me double check that. Times. Yep. And we get 25.0. So we went through, found all the concentrations, and then we had to put it into this final value. So sorry, I kind of stopped there thinking we were done. I guess I was probably hoping that we were done, but we weren't. Now, let me double check everything here. Yeah. Okay, now let's do another one. Same kind of thing. We're given the moles of our reactant, and then we're told how much product we have at equilibrium. So we have to go through our whole ice table, find our concentrations, and plug them into Kc. And our Kc value, I'll save that for later, because you can probably find Kc at this point. We will find it at the end. So let me just write out the expression. Ice table. And we have 4 moles of PCl5 divided by 7. So this is 0.571 molar. Because we have 4 moles in 7 liters. 4 divided by 7 gives us 0.571 molar. We have no products. This is going to be minus x plus x plus x. 0.571 minus x, x, and x. Now they tell us that there's 0.5 moles of chlorine at the end. So 0.5 moles divided by 7 will be x. So x here, the concentration of chlorine is x, and that's equal to 0.5 moles divided by 7 liters. So this is 0.0714 molar. And then once we know x, then we put all of the values, and this ends up being rounding to 0.5 molar. Then this is 0.0714 molar for each of these. And I just want to read the problem through real quick here. Now, Kc for this reaction is the concentration of PCl3 raised to the first power times concentration of chlorine raised to the first power divided by the concentration of PCl5 raised to the first power. And we put our values in. So we have just the numbers. So 0.0714. We have to be in terms of moles per liter. But after that, we forget about the units. You might say, well, if we aren't using units, why do we worry about them? Well, if you could solve this and have this in terms of grams per liter or grams per mil, you did get different numbers. So they have to be in moles per liter, but then we leave them off just to help ourselves out. So we end up with a number rather than, in this case, we'd end up with, if we left the moles per liter in, this answer would have moles per liter. The last one would have been liter squared per mole squared. You don't want to mess with that. You want a number. So once you have moles per liter for your concentration, then leave those units off to get Kc. Sorry, I'm just trying to figure out if I was done here with this, but no, one more. Now consider the reaction given here. Is this right? Yeah. So we have this is actually the Haber process. Its Kc is 12.5. And we're going to assume we're at, you always give the temperature, though we very rarely use it. But the temperature determines what Kc is going to be. So we have to say Kc will change with temperature, so we have to state the temperature. And I'm not that great about it on these problems. On the exam, I always put it in there, and your book always has that in there. But assume that you're always at a constant temperature. Now, determine the equilibrium constant expression and the numerical value for Kc, and I'm going to call this K prime, and I'm going to change these to, just so that they are different. I have K prime here. Notice that the difference here is that everything's been multiplied through by 2. So you might expect, well, since we've multiplied everything through by 2, then the Kc prime value here should be 12.5 times 2. But kind of gave it away there. It's actually squared. So let's might as well. So we're gonna let me write out just so you can see why that is. I'm gonna write out Kc for the first expression, the first reaction above. Now Kc prime is going to be for this reaction where we've multiplied everything through by 2. It's important because if we change, even though this is still a balanced reaction, we end up with a different K value because of those coefficients. Nothing wrong with that. So, well, then how can we trust anything if we can multiply through by the same number, have a balanced equation, and then come up with a different K value? So as long as you know what your reaction was to start with, you'll be fine. But now look at the difference between these two, and this is equal to 12.5. Notice that the difference between these two is that it's Kc squared. That 2 is the number that we've multiplied the reaction through by. If we had multiplied through by 3, this would be a 3 here. If we had multiplied through by 7, that would be a 7. If we multiplied through by 1/2, this would be 1/2, or the square root. So whatever we multiply through by from the original equation, that's what we raise this Kc value to. So this is going to be 12.5 squared. So you can see it. Look at this value. This ratio is equal to 12.5. Look at the difference between these two. This ratio has just been squared. This is a 2, this is a 4. This is a 1, this is a 2. This is a 3, this is a 6. So we just we square the value. So it's 12 point, and this comes up to be 156. So look at this guy. I'm not going to run through the whole explanation again here, but Kc, if we do it out really quickly, you can see we multiplied everything through by 3, and when we put it into the Kc expression, that means that it's Kc, the original Kc, cubed, or 12 point, since we know the value. If we didn't know the value, we'd have to stop there, but since we know its numerical value, we can keep going. This is 1.95 times 10 to the third. Just want to do this out quick. I did these quickly before I can't, yeah. And then the final one here, so make sure I had this on here. Then the final one, Kc triple prime, is going to be NH3 over N2 to the 1/2 power and H2 to the 3/2 power. And let me just write Kc here so you can see. Make sure, yeah, we got plenty of time. Let's see, where is it? Oh, NH. Now, what we've done is we've divided by, let's see, make sure we've gone from 2, the original Kc value, to 1, 1 to 1/2, 3 to 3/2. So what we've done is K triple prime is equal to Kc to the 1/2, or Kc, the square root of Kc. And so that's going to be the square root of 12.5. And apparently that's 3.54 from doing it earlier. So if we take whatever reaction it is, it doesn't have to be this one, any reaction where we have Kc, if we multiply through by any number and it remains balanced, then the new Kc will be just our original Kc raised to whatever, to that power. So whatever we multiplied through by becomes the power. So if we multiply through by 7, we take Kc raised to the 7th power. If we multiply through by 1/100th, then it's to the 1/100th power. Nice and straightforward.